Terminal velocity is one of the rare instances on the MCAT where you'll actually have to consider wind resistance. Most of the time when we talk about falling objects, you could ignore wind resistance, or we assume that things fall at a constant rate of acceleration. In reality, that's not true. What happens when something falls is it starts to accelerate. The force pushing it downward is just your mass times your gravity. So that's the force pushing you downward. As you start to fall towards Earth, there begins to be a force pushing you upward. That equation is roughly 1/2 times your velocity squared times your area times a constant c, which is pretty much a description of how sticky or thick the air is. Now, this second equation is one you don't have to memorize, but it's good to understand the concept. As someone falls, you have two forces acting upon them. You have a force, mass times gravity, pushing them down, and then you have a force, wind resistance, pushing them up. Initially, wind resistance only slows you down. Eventually, you get to a point where the mass times the gravity pushing you down is going to be equal to the wind resistance pushing you up. When that happens, we say you have a net force of 0. And if you look at the equation for force, and that is your force is equal to your mass times your acceleration, if your force is 0, then that means either your mass or your acceleration has to be 0. And since your mass can't change, it essentially means your acceleration is 0. Or you're no longer going faster and faster and faster. Let's look at an example. Here we have two balls being dropped from a tower. Our first ball X is quite big, our second ball Y is small. And just so we can do the math, let's actually assign weights to them. Let's call X 100 kilograms and let's call Y 2. So when they start to fall, it is true that both will start to accelerate at the exact same rate. And if we were on a planet without an atmosphere, or on a place like the moon, both of these balls would fall at the exact same rate forever. But because we live on a planet with wind resistance, eventually we're going to get a force that's going to start to push up. So on X, we want to look at the force that's pulling X down. And that equation is our force is equal to our mass times our gravity. Or in this case, our mass is 100, and as always, gravity is 10. So in our example, our force for X is going to be equal to 1,000. On Y, we have the exact same equation, just with different numbers. Same idea, force is equal to mass times gravity. Our mass is 2, our gravity is 10. So in Y, our force is only 20. Terminal velocity is when your force going down, that's your mass times your gravity, is equal to your 1/2 times your velocity squared times your area times some constant c. There's a lot of things that we can't change in that equation, and there are some things that we can. In the wind velocity equation, we're not going to change the area of the balls. That's constant. In C, that's describing the air, that's going to stay the same as well. The only thing we can change is actually the velocity of the air. So if we look at our two different scenarios, one where the mass times the gravity is 1,000, and the other where the mass times the gravity is 20, if we want to have more wind resistance pushing up, the only way we can do that is to increase our velocity. In summary, both objects initially will start to fall at the exact same rate. However, because X has a larger mass, it's going to require more velocity to slow it down.